So welcome back. This is the second part of Level Up Your Python. One thing I just want to cover really quickly before we get started with the new material. Last time I talked about debuggers, and I was hoping to do a little demo of the visual debugger, because that's just now, as of about 3 days ago, is possible to do that in the regular IPython kernel. So if I'm going back to that 1.4. So what I can do now is I can define a function with a breakpoint. And then if I click this little bug in the top corner, it opens up a new panel. And this is the visual debugger panel. And I just run that function, and that drops me into the visual debugger. So it hit the breakpoint. It's now on this line. I can actually click and make more breakpoints here as well. I can run one line at a time, and I can watch up here and see the local variables changing. This is a list of all the local variables. This is the stack of all the scopes of it's the call stack. So you'll see the outer level scope, and then function, and then whatever function that's called, and what function is that called, etc. List of your breakpoints, and it'll show you the source, which is obviously just over here in my notebook right now. So there's not nothing very exciting over here. And yeah, eventually you'll step here, you'll hit this error. So it actually has a visual debugger now. You used to have a special kernel for that. Now you can just do it in the regular IPython kernel, as long as you have the most recent versions of everything. Okay, let's jump back and start the material for today. So I promised to move fast yesterday, but we moved a little bit slower. Today we are not going to have that luxury, so we're going to be moving pretty quickly. So let's start. We're going to start with decorators and context managers, then we're going to jump to a couple of packages, and then we're going to talk about using packages at the very end. So let's start with decorators. So a decorator is one of the simplest pieces of syntactic sugar you'll see. It is just a tiny, tiny, tiny little bit of characters saved. So this is what it does. If you define now we're just assuming this line. This is the syntactic sugar. Usually you will define a function, and sometimes it'll be a class, but a function or a class. And then you'll run a line like this. So you'll say, and this is kind of strange, because you're getting a function here that takes a function and returns a function. So doing this feels a little bit weird. So instead, you can write it this way. These two expressions are equivalent. When you say at something in front of a function, that will just take the function before it saves the function, it will just pass it through that decorator, that G function. And that's it. It doesn't do anything else. It doesn't even need to return a function. For example, this is a decorator that prints something and then returns 2. Okay, so if I apply it to this function, then it is run, because it's basically running this line up here. And the thing it returned is 2. So F is 2. This is a really bad decorator. Nobody expects to stick a decorator on a function and get 2 instead of a function. But this shows the point that this is really a tiny piece of just syntactic sugar. It's just a different way to write things, but it really transforms the way you think about these. It makes them incredibly useful, whereas this is an extremely strange construct. This is something that just reads beautifully and is very easy to reason about. So for example, there's actually some built-in decorators. One of them is, one of the most common ones is property. There's also class method and static method. So for example, I'm going to do a static method here. I'm going to use a class called bag of functions. I'm going to stick a static method on it. What a static method does is it allows me to call this function sort of, I'll just stick this one on top, the way we would traditionally call it. So this looks like a normal normal instance function, but notice I didn't have to pass self in here. In fact, I can call it without calling it on the class, and it's exactly the same. There's a little bit of magic that's happening with the accessor to allow both of these things to work. So I can treat this class as if it's just this bag of functions, because the class, these functions do not require the instance. They do not even require the class. The class method is a little bit more than that. The class is the first argument, and you can do either one, and you can still access what class you're in. Property is another one you'll see used often a lot of places, and that allows you to define a property. So it looks like a member variable, but it's actually a function that gets run. So this really just, you can treat this like something you would attach to a function that then gives you some feature or something changes in the function. Whereas if you'd use that this syntax, it would have been much more weird passing functions around. And you can also, this thing could be callable. So whenever this is callable, again, it's the exact same, it does the exact same thing. But when it's callable, we call this a decorator factory. And that allows us to add options to the decorator. So another one that you'll find in the standard library is an LRU cache, which is a least recently used cache. And so what that does is it allows you to cache function calls. So for example, I attach this decorator onto this slow function. So I run that. And then say if I do slow 4 seconds, this takes 4 seconds to run. However, if I do it again, it's instant because that's been cached. And you can pass in different options here for the maximum size of this cache that it keeps. And it can also keep track of the types if you ask it to. So using their own example, 3.0 versus 3 will work differently. Whereas right now they would be the same. This is statically typed, but I can pass anything I want in here. I'm asking for an int, and I'm saying I'll return an int, but I technically could pass anything I want in here. Only MyPy will care. So a single dispatch is another useful one. If you need overloading in Python, this gives you one argument overloading. So for example, I define a square function here, but this actually doesn't do anything. It's not implemented. So this thing here is returns this function that has an extra method. And this method can be used as a decorator. So I can say square.register. And square.register lets me register new overloads. So I give it an int, which returns an int. By default, it will actually read this type information and will register something with that type. Though you can manually give it a type if you don't want to use the signature. For example, if you're static typing and your live typing are slightly different, usually they're not, but you can give it options. And I can register a string. So now if I call square on a, oops, need to run that. So if I call square on a 2, I get a 4. And if I call square on a string, I get the little square symbol attached to the string. Okay. There's a few other ones that are built into the standard library. FuncTools total ordering is really useful because that's actually a class decorator. And that means that all you have to do is define 2 of these things. Equals, more than, less than, more than or equals, less than or equals, not equals. We just define 2 of those, and it can't be just the equals and not equals. Then it will compute all of the rest of the ordering methods for you and add them to the class, and you didn't have to touch it. And FuncTools.wraps is occasionally useful. That's actually a decorator that helps you writing decorators. Though there's actually some excellent libraries that do an even better job. Writing decorators we're not going to get into. It's a little bit trickier to write a good one. So data classes is also a really useful thing. You've already seen this, where you just add a data classes decorator on our class, and then it transforms this class and adds all of the things you would need, like the init and buffer and stuff. You could have done that with composition. I'm sorry, with the inheritance, but the decorator is actually better because you're no longer tied to requiring inheritance from data class. You could inherit from something else if you want, and this just modifies the class. So there, those can be a powerful replacement. Click is another. There's lots of third-party ones. We're going to see Numba in a little bit. Click is another one that you basically create command line interfaces entirely through decorators. Okay, so let's move forward. You'll be seeing more of these. We're going to jump to context managers. So just very briefly, I've sort of touched on this a time or two before. This is what sort of context manager has a specific purpose. And it is sort of what I call action at a distance. These are actually really easy to use and write. Decorators are super easy to use, but kind of hard to write. So when you open a file, you need to close it. And context managers give you a way to do that. A del statement is just not reliable enough. But a context manager is extremely reliable. So if I say with open as F, this is probably the most famous example of a context manager in Python, then inside this block, F is open. But when I hit the end of the block, the ending action happens, the closing action happens. And once you leave the block, the file is closed. There are actually some really useful context managers in the context lib. So for example, here's contextlib.suppress. So this will suppress any error that you give it. So if you get a 0 division error, anything that happens inside this block can throw that error, and it will just suppress that. It'll exit and it'll suppress that. So this is sort of like having a try and then catching this and then passing if you caught it. But in a more elegant way with one line. So context managers have the ability to run an action later, and they have an ability to act on a error that gets thrown, an exception that gets thrown. So context managers get sort of information for both things. There's actually a really nice tool in the context manager library called context manager. And that gives you a really easy way to define context managers. And it's a decorator, which is why we had to cover decorators first. So for example, I want to set up a timer. This is something I actually write fairly often. So I do a context manager, then I can define a timer. And then inside this, you just use the word yield, which creates a generator, which we haven't had a chance to talk about. But you just use the word yield, and this is where the inside of the context manager happens. And then when you're done, stuff after the yield runs. And in fact, you can even wrap this in a try and finally, if you want to allow exceptions to go through. So you can even get the exception part of a context manager here. So in this case, I start a timer, then I let the block run. And then at the end, even if there's been an exception, regardless of whether there's an exception or not, I will always print the time. So I printed start, I printed end, and you'll see after this was done, I printed how long this took. So this is actually really useful because you can just do a with timer on something. And it even has the extra benefit. Context Manager automatically provides the context decorator. That's what it uses, which is another tool in there. Context decorator allows you to use any context manager that use this as a decorator too. So I can do timer, and there are no arguments here, so there's no arguments here. And I can attach that to a function, and then I can run the function, and now I have, with exactly the same code, I didn't do anything extra. I also get a nice decorator that times functions. If you are coming from another language, I use Ruby a lot, and JavaScript has this too. It has these tools called blocks, procs, and lambdas. Those are the Ruby names. Ruby literally has all three. But that is not what a decorator is. I'm sorry, that's not what a context manager is. You can't do anything here except run the insides. You can't run the inside of the context multiple times. You can't do anything else. All you can do is allow this to run. Right, so it really is only an action at a distance. It's not, you know, a fancier tool than that. Okay. This is actually the sort of the foundation for the async support in async.io, and that got added to Python in 3.6. And that's really interesting, but we don't use that in HEP that often, so I don't cover that here. And but it uses sort of all of these tools, decorators and context managers and things, and builds on that. All right, so just to quickly answer the question, you can nest decorators as much as you want. That's assuming they're nice decorators and they return something very similar to what you decorated. Absolutely. Click, did a bunch of them. Obviously, if they return 2, then you can't really apply a decorator to the value 2. But yes, you definitely can nest decorators. Most of the standard library ones are designed to be nestable as well. Okay, so we are going to go ahead and jump over to Numba, which is here. So 3.4 if you're running this locally, which hopefully you are. The links are available. Okay, so let's take a look at Numba now that we've covered decorators. And this is a incredible library. It's really taking, and some of the best libraries in Python take what used to be a language and turn them into a library. Pandas does this. Pandas took basically the languages like R and made them available in Python as a library. So you still get all the benefits of running Python and all the Python libraries, and you can do the sorts of things you would normally have done in some other language. Numba does this with just-in-time compiled languages like Julia. So what you can do with Numba is, yeah, I'm going to run that. You can take a function that you would define just in normal Python, and you can add this decorator to it. Numba, there's actually several decorators. I'm using numba.vectorize at the moment. Okay. So again, I wrote just a function here that's operating on a, in this case, this actually just operates on a single value A and a single value B. And I didn't add type information, so you wouldn't think that I'm giving type information to vectorize, which I'm not. But this is really just a single value. This is a single value, but it also happens to work on arrays, so it's a valid ufunc as well. Okay, so I'm going to go ahead and just generate some random data, and I'm going to run that first one, and I'm using time it, so it runs 700 times, and it's roughly 2 milliseconds. Now I'm going to run this just once with the Numba decorator. Now this one time, it took longer because it's doing something. It's just in time compiling this and then running it. So the very first time it took a bit longer. But now let's see what happens when I run this many times. This is doing a full time it loop. So this is times, this is timing it one time. This now took 80 microseconds. So this is now has been compiled into LLVM machine code, and it's running basically at the machine level on the raw types. And you get massive speed ups from this for adding a decorator. And often that's about all you have to do. So this is incredibly powerful, and it actually has a bunch of different things. I showed you the vectorize, and this is actually really nice. NumPy has a vectorize as well, but this allows you to write single element calculations. These don't have to be things that happen to work on arrays. They can just work on single values. This is looping over the entire array in machine code and giving an optimized loop over that that code. Whereas here I had to make sure everything works in a broadcastable way. And if I added the at numpy.vectorize decorator, that loop happens in Python, so it's slow. And you can also do regular functions here. I'll do an example in just a second. You can ahead of time compile this into a library if you want. You can give it the types beforehand, so you actually pass types to this thing, and then it will do the compile step here instead of the first time I call the function. So if you don't like that first call being slower, you just need to tell it what to compile. You can target parallel architectures. You can target GPUs. I think they're retiring the ROCm, and not enough people are using it. I could be wrong there, but it has CUDA support. You can nest. So the next function you'll actually see I do 2 just-in-time compiled things inside of each other. And you can create C function callbacks. This is fantastic and lets you write a C function pointer without ever touching C, which is just, it's pretty incredible. And this is useful in several places in Boosystem and as well as in things. So we're going to do a little example. I usually do other examples. I do a Markov chain Monte Carlo example, which is quite impressive. You'll see that in some of the other materials, so feel free to jump through and look at that. You get, especially for something like a Markov chain Monte Carlo, you get an incredible speed up. So let's just take a look at a ODE. So I'm going to define a function here, this function f, and this is defining an ODE. It's defining a harmonic oscillator here. Okay, and then I'm going to skip this. You can read through this if you're curious, but this is a approximation algorithm here, the Runge 4, and then I'm going to define this in Python. So I have to loop over steps. So this is a loop, but not a huge loop. So this is something that would be kind of nice to be able to compile, but it's not as an easily vectorizable thing. Okay, and then let's just plot that just to prove to you that I'm actually doing something useful. So this is the approximation. I'm actually always kind of impressed at how few points you have to do and how this thing can do very well. If you do,
Chase, just a reminder, 5 minutes left.
Okay. So now I'm going to do this in Numba. So I'm just going to manually call the decorator because I wanted to have both. So this is just the manual expression. Again, I showed you this. That's all the decorator does. So instead of applying the decorator up here, I'm just going to apply them in this line. And then I'm going to run this again. And so by literally doing this, you saw it's the same code. I didn't even bother to go stick a decorator on it. I ran this code here. I've made this over 10 times faster. Okay, and if you want, you can even look at the types there, and they're there. Okay, let's jump to PyBind 11. And this is just a little example of what PyBind 11 looks like. So Numba is really great if you're trying to speed up your own code, but if you're trying to create a fast library, often you want to create something static that you can ship. And so a lot of the libraries in PyHEP are designed this way. And so this is a tool for doing this. And this lets you access C++ libraries. You usually use it to bind, that you can actually just write your code right here, I guess, if you want. And then you write a binding and it looks just like this. So you give it a name and you just pass it the pointer and it infers everything for you and adds it to this module. If you want to compile this, this is sort of what the setup.py would look like. This is what the setup.config would look like. We'll talk about packaging in 2 days. This is an example build system, which grabs PyBind 11 for the build. It's not used at runtime. It's only used to build. And in fact, if you then want to ship this for every known platform, Windows, Mac, and Linux, and all the known versions of Python, this is all you need on GitHub Actions to do that. And that's pretty much almost everything you need in order to ship your little square function that multiplies 2 things. but there's actually a ton more you can do with this. Here's some examples of different of wrapping a class, and things like that. So this supports anything C++ 11 and later. We have specialized support, especially for 14 and 17. Okay. So let's just briefly touch on using packages. We'll sort of cover some of this later as well. So let's spend 3 minutes looking at this. So if you are running a package, if you're installing a package, you'll usually see one of these two things suggested. They're both wrong. This one pretty much never use this. It's better to use this line. This line will install to your user environment if you can't install to wherever you're trying to install to. So it's sort of the equivalent of this, but it's more likely to try to do the right thing. The right thing is to use one of the tools that I'll suggest here, including virtual environments. So if you have an executable, PipX is actually a fantastic tool for running pretty much anything that's an application, anything that's not tied to a specific sort of set of library stuff that you're working on. So if you do pip install pipx, that's the quickest way to get it, or to use brew install pipx or whatever you're using to grab pipx. And then you can now use pipx instead of pip. It actually it sits next to pip. It's pip and pipx are now sort of worked on by the same people. Pipx, you can say pipx install black. You can now run the black command, but you can't import black. Black and its dependencies do not interfere with anything else that you have already installed. You can even run this in one line. This is great for CIs. GitHub Actions and Azure support this. You can just say pipx run, and then that will download and install and run black all in one line, and it'll keep it temporarily for a week and reuse it. If you've used it in less than a week and more than a week, it'll grab it again. So you have sort of a always fresh, but it's cached for quick reruns. So that's probably the most exciting new tool there. If not, you should be using a tools like virtualenv or venv to set up virtual environments and working in there. Okay, so please read through the rest of this. I think there's some useful suggestions here on how to correctly do it. This is the sort of the replacement for pip install, to set up a virtual environment, activate it. Now you can pip install to your heart's content, and it'll all happen only inside this local folder, which is really, really nice.